Okay, let's look at a problem about the electric potential near an infinite charged wire. Here's the setup. Imagine a really long thin wire extending infinitely in both directions placed right along the z-axis. It has a uniform charge spread along its length, which we call the linear charge density symbolized by lambda. The problem asks us to find the potential difference between 2 points that are different distances away from this wire. Specifically, one point is at a radial distance of ρ, and the other is slightly further out at a distance of ρ plus a, where this distance a is much smaller than ρ itself. We need to figure out which of the given options is closest to this potential difference, which we are calling delta V equal to V at ρ plus a minus V at ρ. We are given 4 possible answers for this potential difference, delta V. We'll work through the steps to see which one matches our result. Step 1 is to find the electric field vector E. For an infinitely long, uniformly charged wire, symmetry dictates the electric field is purely radial, pointing straight outward. We use Gauss's law to determine its strength. Applying Gauss's law to a cylindrical surface surrounding the wire and accounting for the radial nature of the field, we solve for the magnitude of E. This yields lambda over 2 pi epsilon naught rho at a distance ρ from the wire. Therefore, the electric field vector is this magnitude in the radial direction, ρ hat. Step 2 is to relate the electric field to the electric potential. We know that the electric field is the negative gradient of the electric potential V. In our case, since the electric field is purely radial, its magnitude E rho is equal to the negative derivative of the potential V with respect to the radial distance ρ. From step 1, we found that E rho is equal to lambda over 2 pi epsilon naught rho. So we can say that the derivative of V with respect to ρ is equal to minus E rho, which is minus lambda over 2 pi epsilon naught rho. Now let's calculate the potential difference delta V using an approximation method. We want to find delta V, which is the potential at ρ plus a minus the potential at ρ. Since a is much smaller than ρ, the change in potential over this small distance a can be approximated using the derivative we just found. Essentially, the change in potential is approximately equal to the rate of change of potential with respect to ρ multiplied by the small change in ρ. Here the change in ρ delta ρ is simply ρ plus a minus ρ, which is just AR. So delta V is approximately equal to the derivative of V with respect to ρ multiplied by A. We substitute the expression for the derivative from step 2, which was minus lambda over 2 pi epsilon naught rho. So delta V is approximately equal to minus lambda over 2 pi epsilon naught rho multiplied by A. This gives us the resulting approximation for delta V as approximately minus lambda over 2 pi epsilon naught times A over rho. Let's quickly look at an alternative way to calculate this, using integration just to be thorough. Step 3, alternative method part 1. We start with the derivative of V with respect to ρ being equal to minus lambda over 2 pi epsilon naught rho. To find the potential V of ρ, we need to integrate this expression with respect to ρ. So V of ρ is the integral of minus lambda over 2 pi epsilon naught rho d rho. When we perform this integration, we get V of ρ equals minus lambda over 2 pi epsilon naught times the natural logarithm of ρ plus a constant of integration c. This constant depends on where we choose our zero potential point, which is arbitrary for an infinite line charge. Continuing with the integration method, we are calculating the potential difference, delta V, which is V evaluated at 2 different points. We substitute the expression we previously found for V of ρ. Notice that the arbitrary constant c cancels out as expected for a potential difference. This leaves us with the difference of logarithms. Using the property that the difference of logarithms is the logarithm of the quotient, we can simplify the expression. Finally, we express the argument of the logarithm as 1 plus a over rho, giving us the final form for delta V. Now for the third part of the alternative method, we have delta V equals minus lambda over 2 pi epsilon naught times the natural log of 1 plus a over rho. Remember, the problem states that a is much smaller than rho. This means that the term a over rho is a very small number. We can use a well-known mathematical approximation for the natural log of 1 plus x when x is very small. The Taylor expansion tells us that the natural log of 1 plus x is approximately equal to x for small x. In our case, x is equal to a over rho. So the natural log of 1 plus a over rho is approximately equal to a over rho. Substituting this back into our expression for delta V, we get delta V is approximately equal to minus lambda over 2 pi epsilon naught times a over rho. As you can see, both the approximation method using the derivative and the integration method using the Taylor expansion give us the same result for when AR is small compared to rho. In conclusion, our calculated potential difference delta V is approximately minus lambda over 2 pi epsilon naught times a over rho. Now let's compare this result with the given options. Option 1 has a over rho squared. Option 2 is minus lambda over 2 pi epsilon naught times A over rho. Option 3 has a positive sign. And option 4 has a over rho squared and a positive sign. Our result matches option 2. Therefore, the potential difference is closest to option 2. And that's our final answer, 2.